Hello and welcome to Eng Phys 2P04 Lecture 24, General Piezoelectrics. Alright, now we're going to be looking at the real coupling in piezoelectrics. In piezoelectricity, we've got that the stress is not just equal to the stiffness times the strain, but rather the stress is equal to the stiffness times the strain minus a coupling coefficient times the electric field. So these are tensors. Once again, we're looking at the tensor notation, and this is the rank 2 stress tensor is equal to the rank 4 stiffness tensor multiplied by the rank 2 strain tensor. Electric field is just a vector, so we need a rank 3 tensor to map this one-dimensional thing to this two-dimensional thing in general. And you could also write this in terms of the strain, giving the strain from the stress as follows here. So now we have a different piezoelectric coupling coefficient called D rather than E. And there's a second pair of equations here. The second equation tells you the charge displacement vector in terms of the electric field and also the either strain or the stress. The first type of equation is called the stress charge form because we've got the stress and charge displacement evaluated in terms of the other things. And the second one is the strain charge form. We've got the strain and charge displacement evaluated in terms of the other things. Notice that we're using different coefficients here. This is because electrodynamics likes to steal all the terms, all the variable names whenever it starts to play with another field. So now we've got electrodynamics saying, no, you can't use E for Young's modulus. E is for electric field, and you can't use epsilon for strain. Epsilon is for permittivity. Electrodynamics was here first, and so it gets to keep all of those coefficients. Right. So anyway, that means that we are left with our second best symbols for all of these things in terms of for the mechanics symbols. So now T is the stress, S is the strain, E is electric field, D is the charge density displacement, C is stiffness, and S is the compliance, but now we're using small letters rather than capital letters because we've got a capital S for the strain. Epsilon is permittivity. E and D are the piezoelectric coupling tensors, which are rank 3. Now, as before, we're not actually going to use this form. We're going to use the Voigt notation version, which is the same thing, but now everything is a vector, and the coefficients are all matrices. Except that, check this out, these ones aren't square. Why is that? Well, because these were rank 3 tensors. They had to map the rank 1 tensor to the other rank 2 tensor, which became a 6x1 vector, but this is a 3x1 vector. So to take a 3x1 vector to a 6x1 vector, we now need a non-square matrix. Right. Okay. So the way that we define it, the E matrix here is actually the transpose of the real E matrix. So we say that the E matrix is a 3x6, and up here is the transpose. So why does this one get the transpose equation and this one gets the non-transposed equation? Well, once again, electrodynamics is winning, and the equation that gives us the charge displacement, even though we're going to be much more concerned with the one that gives us the stress and strain in the same equation, the equation that gives us the charge displacement is the one without the transposed versions. All right. So the coupling coefficients are related as before. Conveniently, here's one situation where it works out in our favor. So we've got that the compliance is still the inverse of the stiffness. Yes, minor victories for mechanics, right? Okay, now the other ones, the piezoelectric coupling coefficients are related to each other through the inverse of the stiffness, which again is the compliance, and the epsilon T, which is the epsilon in the electronics equation that has a stress in it, is related to the epsilon S, the one in the equation with the capital S in it for strain, through this equation, through the coupling coefficients. Okay, so the T inside the variable, inside the brackets, now is part of a variable name. Everything inside these square brackets here is what I'm using to distinguish matrices from vectors. The T outside is a symbol for transpose. So this means matrix transpose of this D matrix here. And this means matrix transpose of the E matrix, but inside here, the T means just epsilon T, the stress version of epsilon, rather than the strain version up here. Okay, so once again, two necessary conditions for piezoelectricity are different charges on the atoms and crystal asymmetry. The combination of both of these things can give rise to coupling matrices like the ones for quartz. So what haven't we seen for quartz before? We haven't seen the piezoelectric coupling coefficients. We have seen the compliance tensor. This is old news for us at this point. And we haven't bothered with the permittivity, but there's nothing too scary about its permittivity matrix. This just, quartz isn't asymmetric enough to map electric fields in X to charge displacements in Y or anything like that, unless we're also applying appropriate boundary conditions and exploiting its piezoelectricity. So maybe if we let the electric fields in X lead to strains that may mean the material deforms in a certain way, then we might get maybe we'll get a field building up in Y potentially. So let's see how this plays out. It's easier to see how this works by looking at the equation we're more familiar with, which is this first one here. So the strain is equal to the compliance times the stress plus D transpose times E. And the problem is we're looking at D, but we need D transpose. So let's take the transpose and write that out, substituting into this equation. Let's look how quartz behaves. So if quartz is free, all of these things are zero, then we'll figure out what kind of stresses we get in response to electric fields. Considering how this would multiply out, you can see that X-directed electric fields, E1 here, are going to, through this negative 2.3 term, lead to X strains. And they're also going to lead to Y strains through this positive 2.3 term. But because there's zeros here and zeros here, electric fields rather, don't lead to Z strains, and Y and Z electric fields don't lead to any kind of axial strain, although the Y-directed electric fields do lead to shear strains from this term. Z-directed electric fields do nothing for quartz. Okay, now quartz is actually still quite a complicated material. We can deal with easier materials like PZT, the one we were looking at last time. So here's the types of entries that can be non-zero for piezoelectric materials in the same crystal class, 4mm, as PZT is. Here specifically are the matrices for PZT. So last time we dealt with PZT by saying that it had Z-directed electric fields coupling to strains in X, Y, and Z, given by these three numbers, and you can see why now, since we have this coefficient matrix. In last lecture, we didn't actually apply electric fields in the X or Y direction for PZT, but you can see now that they don't actually lead to axial strains, although they do lead to shear strains because of these components. Okay. First thing that we're going to do is use the formulas that we had up earlier. So this set of proofs of formulas, or this set of formulas, to translate between the stress charge coefficients and the strain charge coefficients. Oftentimes when you look this up, any one source will only have the stress charge coefficients or only the strain charge coefficients, but for different purposes you're going to need both sets of coefficients. So first thing we're going to do is calculate PZT5A's stress charge coefficients, the ones in here, from the strain charge coefficients, the ones in here, presented below. Okay, so here's the script to do just that. What I'm going to do is type them in as S matrix, D matrix, and epsilon T. Then the C matrix is the inverse of the S matrix. The E matrix is the D matrix right multiplied by the C matrix. And epsilon S is epsilon T minus the E matrix multiplied by the S matrix multiplied by the transpose of the E matrix. And here they all are. In here I used interface display precision equals 4 because without that, these at least my version of Maple is outputting like 8 or 10 decimal points, and it's impossible to copy this over and have it stay looking any semblance of nice. So if one weird quirk of this is that if something doesn't show up in scientific notation, then it it can truncate values, and so you may want to turn this off or adjust the precision depending on what you're using and what kind of result you're getting. Note that this is not the same as just setting Maple's global variable digits equal to 4. Digits is the number of digits that it uses to make calculations. So it's still using a large number of digits, maybe 10 or 12 or 15 or something, to make these calculations, but it's displaying 4 when it's done with all of that. Next example, rectifying simplified and general piezoelectricity. In lecture 23, we did some piezoelectric calculations, and you did some more in the examples. We did PZT5A's response to electric fields in the Z direction by saying the piezo strain was just this, and then used it to calculate mechanical strain, and then used that and the stiffness matrix to calculate stress. Rectify this with using the constitutive equations that we did above to modify Hooke's law directly. Right, so in other words, just see how this approach fits into the more general approach we're presenting here, and how they both can still work. Well, in lecture 23, we said stress was just the stiffness times the mechanical strain, where mechanical strain was the actual strain minus the piezo strain, and the piezo strain was this. So we didn't bother to write out the shear terms, but now if we include them, they were just 0 because we didn't add on to any shear. But notice now that if the electric field is just in the Z direction, then taking D transpose for PZT multiplied by that electric field gives us this matrix, which is what we said. So then our mechanical strain was just equal to the actual strain minus dt times the electric field. Okay, well that's great. So that seems like it should be justified. Can we then substitute this into the stress equation that we used and see if we get something back? See if it agrees with our constitutive equations? Sure, why not? So let's take Sm, the mechanical strain, and substitute it into here. When we do that, we have that the equation we used was stress equals stiffness times mechanical strain, where mechanical strain is actual strain minus the transpose of the piezoelectric coupling coefficient matrix and the electric field, carrying this matrix multiplication through, and then factoring the transpose out, remembering that it reverses the matrix order. We can say, hey, D right multiplied by the stiffness matrix was just the other coefficient matrix, and now then our equation has reduced to the stress charge equation. So that means we've got two options for using piezoelectric calculations. We can either do what we did in lecture 23 by defining a mechanical strain as actual minus piezo strain, and then just use that to calculate stress from Hooke's law, or just define the actual strain and use the stress charge form of the constitutive equations instead of Hooke's law. Next example problem, forward piezoelectric effect. Suppose that a block of PZT5A has dimensions same as before and electrodes on its opposite Z faces, so across this 1 millimeter face. 1 millimeter thick distance. However, unlike in the previous question involving this PZT slab, instead of hooking up the plates to a voltage supply and setting a fixed voltage and therefore setting a fixed field, we're going to hook them up to a voltmeter, one with infinite resistance, so an ideal voltmeter that draws no current, meaning no charge transfers to or from the electrodes, so that the charge displacement vector stays 0. Suppose also that the slab is unconstrained and a 50 kilogram person steps on it, distributing their 500 Newton weight evenly over the Z surface. How much voltage shows up on the voltmeter? Then what are the total strains of the PZT slab in X, Y, and Z? And what's the effective stiffness of unconstrained PZT in the Z direction when the top and bottom plates are first electrically isolated so that D is 0, and then grounded so that E is 0? Okay, so by having this person's weight on the top surface and having it otherwise free, we have a known stress in all of the different dimensions. We've got a compressive Z stress and no stress in X or Y. And knowing the stress lets us calculate the charge, the electric field, since we also know that the charge displacement is 0, since we're not hooking up any wires to allow charge to flow onto the object from the outside or anything. And we're not applying any electric field. So we get an electric field that's equal to this result of this multiplication. And the electric field ends up being 2.4 megavolts per meter. And given the distance of 1 millimeter that it's extended over, this means a voltage difference of negative 2400 volts at the top plate relative to the bottom plate. Okay, the strains, now that we know these, this stress, just turns out to be, you can do this either with the constitutive equations or calculate the mechanical strain and then add that to the piezo strain as we're doing here. You could also have used the constitutive equations, no problem if you do it that way. Okay, so this voltage, this electric field that we've got, is reducing the strains that we've got, that we would get. The part of stepping on the surface, building up this stress, manifests in a physical movement, and part of it manifests in an electric field generation. From our work in parts A and B, we can calculate the effective stiffness as the stress divided by the strain. And in when D is fixed to 0, as we dealt with in this problem, the effective stiffness is 102 gigapascals. But when E was equal to 0, then it's just 1 over S33 for PZT, which is 53 gigapascals. So the material is much stiffer if you don't allow if you don't allow charges to move from the top plate to the bottom plate or vice versa in order to balance out the electric field that you create by stressing it. FlexPDE piezoelectricity. Using the previous example as a guide, modify a FlexPDE script to perform piezoelectric calculations using either mechanical, actual, and piezoelectric strain, so the 3 different strain definitions, or just use the constitutive equations. Okay, so using the 3 strain definitions, we've got strain defined as the electric field left multiplied by the transpose of this coupling coefficient matrix. And then our actual strain is defined the same as before. Piezoelectric strain now a new thing, defining EXP, EYP, EZP, and the same thing for shear. And then we need to define mechanical strain as the actual strain minus piezoelectric, same thing for shear. And then Hooke's law, actually the same as it was in the thermal section, except now we can have mechanical shear strain being different than actual shear strain. For the second approach, where we're using the constitutive equations to incorporate it into FlexPDE, let's use the stress equation from the stress charge form. Then we've got that the actual strain is defined the same as before, and the constitutive equations can just be typed in directly in place of Hooke's law. So now we've got, it's a fair bit less equations, so we only need 2 sets of equations in this method rather than 4. Although it's a little bit more difficult to incorporate temperature into it in the same way. I suggest you use whichever method makes the most sense to you, and then after you've done a couple of problems, come back and try and code the other way just to make sure that you've got all your bases covered. Certain problems may be easier for you to understand from one approach, and other problems may be easier from the other approach. Now, in the most recent example before this one, where we solved the forward piezoelectric effect, when we know that D is 0, for instance, and we don't actually know what E is at the start, but we need to solve for it, then what you're going to want to do is use one of these equations to write E in terms of the known D, and either this stress or the strain. You can put it in terms of either one of these, and then the code should still work, because if you put it in terms of stress, then this just becomes an equation that has some stress on the left, but then some coefficients in front of stress on the right, and FlexPDE can solve for that. If you put it in terms of strain, then it's just got some strains here and then some extra strains added here. No problem.